Now let's talk about how we can solve this problem using binary search. So we consider this example. The middle index here is 2, and according to this case the value of I is less than a of I. So considering this case, we have to reduce the value of high to mid minus 1, and in case the value of I is greater than a of I, we have to increase the value of low to mid plus 1. Now if we talk about this case, we will notice that as we go from this middle element to the right hand side, the value of a of I can increase by plus 1 up to n plus 1, but the value of I will only increase by plus 1. So the value of a of I will always be greater than I as we go to the right hand side. So there can never be a case that these two values are equal. That's why we are checking on the left hand side by reducing the high to mid minus 1. And now if we talk about this case, here the value of a of I is less than index, which means as we go to the right hand side there could be a chance that these two values can be equal, and that's because of the same reason as this. The index can increase only by 1, but the a of I can increase by n plus 1. So as we go to the right hand side, this value can be greater or equal to I. So that's why here we are going to check on the right hand side by increasing the low to mid plus 1. So here we have a variable list which is a sorted array, and I'm going to write the typical logic of a binary search. So I'll write in low equals to 0. I'll make use of another variable high, which will be the last index. So array size minus 1. Let's find out the array size, and equal to size of list divided by list 0. Now we have to make use of a loop while low is less than equal to high, and we'll find out the middle index, and mid is equal to low plus high by 2. So we'll check if this mid is equal to the value at mid, which is list mid. So in this case we'll store the value of mid in variable. I'll name it R, and we'll break the loop, and here we'll return or print the variable R. So if the mid is not equal to the element at this index, we'll check if the mid is less than its value. So now in this case the element is greater than its index, which means if we go to the right hand side, all the elements are going to be greater than the index. So in this case we have to look for this fixed point on the left hand side, and for which we have to reduce the high So I'll write high is equal to mid minus 1, else we will increase the low to low plus 1. Okay, now let's run this code, and the output is 0. So this is the index 0, 1, 2, 3, 4 and 5. So there is no fixed point in this array, so we have returned 0. Now let's check with this next array. So again the input is 0, which is fine because this is the index 0, 1, 2, 3 and 4. So the fixed point is this 0. Let's consider this third example. So this is index 0, 1, 2, 3 and 4. So as you can see, the fixed point is 3. So our answer should be 3 in this case. So we have got a correct result, and this was how you make use of binary search to find a fixed point in a distinct sorted array. So in my next video, I'll talk about this question, which is searching in a rotated sorted array. So thank you so much for watching, and I also want to request you guys to please subscribe. So thank you so much and have a great day.